Hello everyone, and welcome back. Today we're just going to give a brief overview of the basic principles that you definitely should know when it comes to p-values and test statistics associated to distributions that are based on sampling from normal distributions, which often can be summarized via the z, t, chi-square, and f distributions. So let's just start off with the very basic one that everybody definitely should know, and that's the claim that the population mean is equal to some particular value. Let's call that mu0. So we should know how to test this with a two-sided alternative hypothesis, but when it comes to a one-sided alternative hypothesis, usually the only difference when it comes to p-values and test statistics is just the p-value is half of what the two-tailed p-value would be equal to. So we're going to be assuming that we're sampling from a normally distributed population with some mean mu and some population variance sigma squared. And of course, we do not know what mu and sigma squared is, generally speaking, but in some circumstances, we actually do know what the population variance is equal to. So if we're approximating the population mean mu, we need ideally an unbiased point estimate for that. So an unbiased point estimate for mu, of course, would be the sample mean x bar. So although this is an unbiased point estimate for the population mean mu, there is some error associated with that point estimate, and we usually represent that error as standard error or SEX bar. So if you know the population standard deviation, one can show that the standard error for that point estimate is sigma divided by the square root of m. But if you do not know what sigma is, we can approximate sigma with the sample standard deviation, and then our standard error for x bar then takes that particular form, s divided by the square root of m. In the scenario where you actually do know sigma, we're usually going to be only using a z critical value, and if you do not know the standard deviation of the population, then that would be a t critical value. So that's pretty much the flow chart that you need to understand, where the t value is going to have a degrees of freedom equal to the sample size that you've drawn minus 1. So let's look at a brief example of, how we would construct these particular things. So let's assume that we have a test statistic that's a z test statistic, which is given by, generally speaking, x bar minus mu0 divided by the standard error, which can also be written as x bar minus mu0 divided by. So if I'm saying this is a z test statistic, that means the standard error is going to be sigma divided by the square root of m. And let's just pretend that this is equal to 2.9628. So ideally, if we want to reject the null hypothesis that mu is equal to mu0, then we want our point estimate to be as far away from mu0 as possible. So when we look at our z distribution or standard normal distribution, we would like this test statistic to be as large as possible, either in the positive regime or the negative regime, since we're working with a two-tailed alternative. So how large is large? Well, usually we're going to be comparing that blue star to a critical value which is located somewhere in the interior regime, where the area between that is going to be equal to c, and the area to the left of c would be alpha over 2, and the area to the right of c would be alpha over 2, right? So that would be that entire area and that entire area. So usually what we would like to calculate is a p-value, because if the p-value is less than alpha, that means we have evidence to believe that our test statistic is far enough from 0. In particular, that implies that x bar is significantly far from the claimed value of mu. So from a test statistic, we can calculate a p-value from the z distribution. In Excel, for a z p-value that's two-sided, it would be 2 times norm dot s dot dist of the left version of that test statistic, which is negative 2.9628, comma, true. So once we calculate that, we can find that's approximately equal to 0.0031. So if you're working with an alpha value of 0.05, then we see that our p-value is less than that alpha value. Therefore, we have evidence to believe that our population mean mu is not equal to that claimed value mu0, and therefore we believe that the population mean mu is actually something other than that claimed value of mu. So that's the main structure of test statistics. Now let's look at a particular example where we have a couple numbers coming from our samples. So let's assume We gather a sample, and that sample has the following summary statistics. So let's assume that the sample size is equal to 31. Let's assume that the sample mean is equal to 36.5. Let's assume that the sample standard deviation is 2.61. And let's assume that someone claims that the population mean mu is equal to 35.7. And let's test that claim with a two-sided alternative that 35.7 is not equal to the population mean mu. So notice that I have not given the population standard deviation. That means we're going to be using a t-test statistic and a t-critical value and a t-p-value in this circumstance. So our t-test statistic is going to be equal to, again, x bar minus mu 0 divided by the standard error associated to the point estimate for the population mean mu, which in this circumstance is going to be x bar minus mu 0 divided by s divided by the square root of m. So once we substitute the value of x bar, the claim value of mu, which is given to be 35.7, the sample standard deviation, and the sample size of 31, you can find that this is approximately equal to 1.7066. So notice that our claim value is 35.7 and our point estimate is 36.5. And from the t-test statistic approach, their difference, at least in the normal world, is approximately 1.7. So is that substantially large? Well, we can calculate a p-value and then see if that p-value is small enough to reject this particular claim. So the p-value for the t-world in a two-tailed alternative is going to be equal to 2 times t.dist of the negative version, or the left-tailed version of our test statistic, so negative 1.7066, comma, our degrees of freedom, which is going to be our sample size minus 1, comma, true, and you can find that that's approximately equal to 0.0982. So let's assume that we're working with an alpha value of, again, 0.05, but you could, of course, be working with a higher or lower value of this. But if this is the alpha value that you are working with, notice that our p-value is greater than that alpha value. That means our p-value is not small enough. Therefore, we fail to reject the null hypothesis that the population mean mu is equal to 35.7. Therefore, we have evidence to believe that the population mean mu is actually equal to 35.7 or something close to it. Now, there is one other circumstance that you may encounter in the realm of hypothesis testing for the population mean mu. So let's look at that particular scenario. So let's assume that we have a sample whose test statistics are given by a sample size of 32, a sample mean of 26.2, a sample standard deviation of 2.1. Let's assume that we're sampling from a normal distribution, but let's also assume that we know the population size of n, and that's 35. So we have 32 out of the total 35 members in our population, which is a significantly large proportion. So let's assume that someone claims that the population mean mu is equal to 28. So that's what mu 0 is going to be equal to. So what is the significance of knowing the population size? Well, in that case, that means we can include the finite population correction factor into our standard error calculations. So remember that the finite population correction factor is given by the square root of capital N minus little n over capital N minus 1. So using our sample size and our given population size, you can find that that's approximately equal to 0.2970. One can show that regardless of the sample size and the population size, as long as the population size is bigger than 1, the FPC is always going to be between 0 and 1. So it's always going to make your standard error closer to 0. So now that we have our finite population correction factor, we can calculate our standard error for x bar, which again, since we do not know sigma, that's going to be equal to s divided by the square root of m. And since we know our capital M, we're going to be multiplying by our finite population correction factor, and you can find that that product is approximately equal to 0.1103. Once you have that, we can calculate our t-test statistic since we do not know sigma. So t-stat is going to be equal to, again, x bar minus the claim value of the mean divided by the standard error that we just calculated, and that's going to come out to approximately negative 16.32, which is, in most circumstances, extremely far in the left tail. So one can find, same as before, that the p-value from Excel is going to come out to approximately 8.98 times 10 to the minus 7, which most people would usually say is approximately equal to 0, because it's definitely less than even 1%, which is even substantially less than 5%. So since our p-value is technically sufficiently smaller than any value alpha for which you can give, that means we're going to be rejecting the null hypothesis that the mu was equal to 28, right? And that's actually one of the very good things about including the finite population correction factor, because if we have more of the population, then that should make our standard error smaller, because once we have the entire population in our hands, our standard error should be equal to 0 for all of our calculations. The next set of hypothesis tests that I want to focus on would be testing the claimed value of a proportion, the equality of two proportions, and the equality of two population variances. I think these three tests are pretty easy to take care of. So let's assume that we have a population proportion P. And keep in mind the population proportion P is equal to the total number of successes in your population divided by the total population size. And we're going to be approximating this with a point estimate P hat, which is equal to the number of successes in our sample divided by our sample size that we collect from our sample. All right, so that has to come from a sample, and it's very important that these two criteria hold. The first thing is the responses must be independent of one another, and the sample size must be substantially bigger than 0. In terms of how large is substantially large, some people require that the number of successes be bigger than 10, the number of failures in our sample also be bigger than 10, and merging these two together means that our sample size must be more than 20. Those are some of the common rules that people usually use. So there's a nice little theorem that says, and this theorem is usually referred to as the de Moivre-Laplace theorem. And the de Moivre-Laplace theorem says if our sample size is substantially large, then we can use a normal distribution to approximate a binomial distribution, where a binomial distribution is actually what this random variable is taking, because x is the number of successes in a finite sequence of Bernoulli trials. We're assuming independence, therefore p hat is in some sense a binomial random variable. So if we can approximate a binomial random variable with a normal random variable, we can use z critical values, z test statistics, and z p-values to analyze the hypothesis test that a proportion is equal to some particular value that's usually taken to be between 0 and 1, typically non-inclusive of those boundaries. Right? So what is the standard error for a sample proportion? So one can show that the standard error for a sample proportion is going to be equal to the square root of the population proportion times 1 minus the population proportion divided by m. But how can we use the standard error of a sample proportion that requires the population proportion in order to estimate the proportion? Typically, we can't. Therefore, a walled approximation for this standard error is using the fact that p hat is an unbiased estimator for p. Therefore, one can say that this is going to be approximately equal to p hat times 1 minus p hat divided by m, where again p hat is our sample proportion. So once you have your standard of error, then we can calculate our z-test statistic, which is going to be z-stat is equal to p hat minus p0 divided by the standard error of p hat, and then we can calculate a p-value from this test statistic, just like we did for the population mean testing. Another hypothesis test that you may want to conduct is seeing if there's a significant difference between the percentages or proportions between two different populations. For example, the percentage of happy people in city 1 and the percentage of happy people in city 2. So in this particular scenario, now we have two parameters that we're sort of estimating the equality of. So a natural thing to do is to create a single parameter, which is going to be the difference in population proportions, which we can define as P1 minus P2. You could also do P2 minus P1. You will get equivalent conclusions from any of the test hypothesis strategies that you may know, confidence intervals, test statistics, p-values. The only difference is your test statistic will be sometimes reversed, your confidence interval will be mirrored, but your p-value will remain the same in either direction. So if this is our new parameter, that turns our null hypothesis into PD is equal to 0 and PD is not equal to 0. So in some sense, we're still testing a single proportion like we did before, and we should be able to know how to sort of conduct this. We just need a point estimate for PD, which is going to be equal to P hat D, which is the difference between sample proportions, and it's very important to note that this has to be in the same direction. So if you define PD as 2 minus 1, then P hat D should be P hat 2 minus P hat 1. As long as you stay consistent, you shouldn't have any issues. So what is the standard error for this point estimate P hat D? One should be able to show that this is going to be equal to P hat 1 times 1 minus P hat 1 divided by the sample size 1, and then P hat 2 minus 1 hat P hat 2 all divided by N2. Again, each of these samples must have the criteria that the number of successes and failures in each of them must be greater than 10, both samples must be greater than 20, the responses in each of the samples must be independent of each other, and the samples themselves must be independent of each other as well. So once you have your standard error, then we can use a z-critical value to approximate the distribution that this proportion is holding because our sample size is sufficiently large. So our test statistic is going to be a z-test statistic, and then we're going to have our point estimate p hat d minus the claimed value of the difference between the proportions divided by the standard error of that point estimate that we're using. Typically speaking, since we're comparing this to 0, that would be equal to 0, just leaving us with p hat d in the numerator of that test statistic. And since we're using a z-test statistic, we will be using our p-values with the z distribution, just like we did with the single proportion and the mean testing when the sigma was actually known. Another hypothesis test that is pretty straightforward to use would be the equality of variances, which is sometimes referred to as an f-test, provided that we are sampling again from two normally distributed populations. Again, we are working with two parameters here, so we're going to be creating a single parameter, which I'm going to call sigma q squared, which is going to be equal to the quotient of our population variances. And what we're going to do is we're going to mandate that this quotient be greater than or equal to 1. So in this particular scenario, our f-test statistic that we're going to be using here is going to be equal to the sample quotient of sample variances, which is going to be equal to s1 squared over s2 squared, which again we're going to mandate to be equal to greater than or equal to 1. So whichever variance you have that is larger in your sample variances, we're going to put the larger variance on top and the smaller variance on bottom, so your f statistic will always be greater than or equal to 1 by design. So therefore, the alternative hypothesis that we're actually working with is not a two-tailed, but actually it's going to be a one-tailed, because we're mandating that sigma 1 squared is significantly greater than sigma 2 squared. So let's look at a numerical example to sort of see how that would look like. So let's assume that we construct a sample, or sample 1 and sample 2, and our samples sort of have the following test statistics. Our sample variance for 1 is going to be 3.8. Our sample variance for sample 2 is going to be equal to 4.3. And let's assume that our sample size 1 is equal to 18 and our sample size 2 is going to be equal to 14. So what would be our f-test statistic in this scenario? So our f-test statistic is going to be the larger variance divided by the smaller variance. So that's going to be equal to 4.3 divided by 3.8, which is going to be approximately 1.1316. Now, what is the degrees of freedom that we're going to be using here? So the degrees of freedom for the top is going to be the sample size of the top sample reference minus 1. So 4.3 is associated to sample 2, so its sample size was 14. So the degrees of freedom of the top is going to be equal to 13. And the bottom degrees of freedom is referencing the second sample, which is equal to 18. So the degrees of freedom for the bottom is going to be equal to 18 minus 1, which is going to be equal to 17. Therefore, if we want to calculate our right tail distribution p-value, how would we go about that? Because if these population variances are equal to each other, then the quotient of these population variances is going to be equal to 1. Therefore, the closer the sample variance quotient is to 1, the more evidence we have to believe that the population variances are exactly equal to or even approximately equal to 1. So if the variance quotient is significantly greater than 1, then we have evidence to believe that they are substantially different from each other. So is 1.13 substantially bigger than 1? Well, we can look at a p-value and sort of determine that on our own. So our p-value is not going to have a 2 times because this is a one-tailed test and then a two-tailed test. And in Excel, you can do f.dist.rt for the right tail of our f test statistic. You don't have to put a negative value there because f statistics are never negative, and then it's going to be the degrees of freedom for the top, comma, the degrees of freedom for the bottom, and then comma true, and that's going to come out to approximately 0.3985 for our example. So since this p-value is typically not substantially small, unless you're working with an alpha value of at least, say, 38%, that's usually not going to be small because it's definitely not smaller than 5%. So since it's not small enough to reject the null hypothesis, that means we're going to fail to reject the null hypothesis that the variances are actually equal to each other, which means we have evidence to believe that they are equal to each other. Therefore, we have evidence to believe that population 1 and population 2 are homoscedastic to one another. If we have evidence to believe that they are different, then we usually say that these populations are heteroscedastic to one another. But this test for equality of variances is usually referred to the F test for equality of variances, which is one of the few tests that we actually most of the time always use a one-tailed or more over a right-tailed test in order to test it. Instead of comparing two variances to one another, let's assume we're interested in comparing one variance to a claimed value. For example, somebody claims that the variance of a population is equal to 10 or some other number, which we're going to call sigma squared 0. So the test statistic that we're going to be using here, assuming that we're sampling from a normally distributed population, is going to be associated to a chi-square distribution. So the chi-square test statistic that we're going to be using here is going to be equal to v times s squared divided by the claim value of the variance. Now, since we're working with a two-tailed alternative here, we need another test statistic to be working with. So in order to construct our second test statistic, we're going to sort of treat this like an F distribution, even though sigma squared 0 is not a random variable, it's a number. So what we can do is we can sort of hybridize this and treat s squared as our fixed value and sigma squared 0 as our random variable, and then consider sigma 0 squared divided by s squared here. Right? And in each of these situations, we're going to be assuming that v is equal to n minus 1. Okay, so our goal in terms of rejection is to have that the sample variance be substantially larger than the claimed value, or that our sample variance be substantially less than the claimed value. That's why we need these two different numbers to sort of compare. So if we look at our distribution of the chi-square distribution and sort of see what's going on here, so as long as it's substantially larger or substantially larger than the other, in particular far from a quotient of 1 without considering that degrees of freedom v in the front, then as long as it's substantially small, then it's okay. And as long as it's substantially farther than 1, it's also okay as well. For example, let's call this chi-squared 1 and chi-squared 2, where chi-squared 1 is the minimum of these two values, 1 and 2, and chi-squared 2 is the maximum value of chi-square stat 1 and chi-square stat 2. So the p-value in this particular picture would be the area to the left of chi-square 1 and the area to the right of chi-square 2. So one could see this, at least in the graphical perspective, that the p-value, if this is, say, the c-axis, is going to be equal to the probability that c is less than chi-squared 1 plus the probability that c is greater than chi-squared 2. And one could be like, oh, what if I just focus on the interior portion? And definitely you can. That would be equivalent to the probability that c is in between chi-squared 1 and chi-squared 2. So how exactly would you do this in Excel? So for example, the probability that c is less than chi-squared 1 is going to be equal to CHISQ dot dist of our chi-squared 1 value, our degrees of freedom, comma true, and then plus that particular value, which is the complement of the left-tailed version, which is going to be equal to 1 minus the chi-squared dot dist value of chi-squared 2 dot v comma true. Right? And technically we don't need that bracket, so I'm not going to overcomplicate that here. Okay, so if we sort of rearrange this, what exactly do we have? So the p-value for a chi-squared test is just going to be equal to 1 let's do it 1 minus, actually let's do it this way, 1 minus chi squared dot dist. Let's actually do a bracket here just to make it nice. Chi squared dot dist of chi squared 2 v comma true, and then minus chi squared dot dist chi squared 1 v comma true. And then pretty much what we have here, if you're familiar with calculus, this is just going to be 1 minus, for example, the integral from chi squared 1 to chi squared 2 of the chi squared density function, right? So if you sort of see here, this is 1 minus the antiderivative of b minus the antiderivative of a. But if you don't really care about that, that's perfectly fine. But in Excel, that will serve your needs for this particular hypothesis test. The next test that we're going to consider is seen in a variety of different fields, and that's testing the equality of two population means. Again, we're working with two parameters, so it's very useful to define a single parameter to sort of compare the two. So let's define this as mu1 minus mu2, which is going to turn our null hypothesis into the difference between them is equal to 0, and the difference between them is not equal to 0. So in this particular case, 0 is the claimed value of the difference. So the tests for equality of means typically come in three different categories. So the first case is what we refer to as the paired difference. Generally speaking, it's a t-test. There are special cases where it is a z-test, but most of the time it's going to be a t-test. So a paired difference t-test is usually evident if you have, for example, one population here, one population here, and there's a one-to-one correspondence that has a meaningful relationship to the study at hand. For example, this is extremely common with before and after studies. So for example, if you have a one-to-one correspondence, what you can do is we can construct a set of differences between them. For example, you can do the happiness that you have today minus the happiness you have yesterday, and do that for everyone in a sample. And then you're going to have a bunch of differences, for example, D1, D2 down to say D little m. So this population of differences, which is of course going to turn into a sample of differences, is going to have, for example, a sample mean of differences and a sample standard deviation of differences, which you can easily calculate by doing the differences and then doing the mean and standard deviation of those particular values. Once you have these sample test statistics, x bar d and little sd, then you can calculate the standard error of the point estimate for mu d, which one can show is going to be x bar d, which is going to be equal to the standard deviation of the differences divided by the square root of the number of pairs that you have in your pair difference t-test. So since we usually don't know the standard deviation of all the differences, that's why we're going to be using a t critical value here. Since we're using a t critical value here, we have to know degrees of freedom, and then in this particular case, the degrees of freedom is going to be the number of pairs minus 1. Now let us look at case 2. So what is the difference between case 1 and case 2 and 3? Case 2 and case 3 both work with independent samples. So both of these work with independent samples, where case 1 deals with dependent samples only. So case 2 can be viewed as what we call the pooled variance t-test, and case 3 is what we refer to as the unpooled variance t-test. So how do you know which one to use? So you will use the pooled variance t-test if, for example, the f-test, which again is sigma 1 squared is equal to sigma 2 squared. So if you have evidence to believe that these are equal to each other, then you're going to be using a pooled variance t-test. Therefore, your goal is to fail to reject the f-test if you want to have evidence to believe that they are equal to each other. If you have evidence to believe that they are equal to each other, a pooled variance t-test is what you're going to be working with. Now again, if you do a f-test for the equality of variances and you reject that particular null hypothesis, then you have evidence to believe that those variances are different. So in that scenario, you will be using an unpooled variance t-test. So the first thing in a pooled variance t-test that you need to calculate is going to be what we call the pooled variance, which is going to be equal to v1 s1 squared plus v2 s2 squared, or nu1 and nu2 if you're looking at this from the Greek perspective, divided by nu1 plus nu2, which some people just call nu. Once you have your pooled standard deviation, then you can calculate your pooled variance, then you can calculate your pooled standard deviation, which is going to be the square root of your pooled variance. And then you can calculate your standard error for the difference in means to be equal to the pooled standard deviation times the square root of the sum of the reciprocal sample sizes, 1 over n1 plus 1 over n2. Now, in the unpooled variance world, you don't need to calculate a pooled variance, which is actually pretty nice. You can actually directly calculate the standard error of x bar d to be equal to the square root of s1 squared over n1 plus s2 squared over n2. So it's actually pretty nicer than the pooled variance perspective. Now, the degrees of freedom, because we're still going to be using a t-test statistic for both of them, is going to have different degrees of freedom. So the degrees of freedom for a pooled variance t-test is going to be equal to v1 plus v2, the degrees of freedom, or the denominator of the pooled variance, and the degrees of freedom for the unpooled is a slightly messy, but this is going to be equal to the standard error associated to the point estimate for x bar d in the unpooled world to the power of 4, all divided by s1 to the power of 4 all over n1 squared v1 plus s2 to the power of 4 divided by n2 squared times v1. Right? So in some sense that is a weighted degrees of freedom. So once you have your degrees of freedom for both of either case 1, case 2, or case 3, and you have calculated the appropriate standard error, then you can calculate your t-test statistic regardless of which world you're in. So that's going to be equal to x bar d, our point estimate for mu d, minus the claim value of the population mean difference, divided by the standard error of the point estimate that you've calculated. And typically speaking, since we're just trying to see if there's a significant difference between them, most of the time this is going to be taken to be equal to 0. So again, we're just going to have the point estimate on the top, most of the time, divided by our standard error. And that's how you can conduct the 3 most common t-tests for the equality of population means. The last thing I want to talk about today is 3 hypothesis tests that are often associated with basic, simple linear regression. So again, let's assume that we have what we call predictor variables sampled from a population and y a particular response from that. And let's assume that this is coming from a bivariate normal distribution. So both x and y are normally distributed, and let's assume that we are claiming that x and y are linearly correlated as well. That is, there exist these numbers beta 0 and beta 1 such that y is equal to beta 0 plus beta 1 x1 plus some residual associated to that value. Right? So at least from the prediction perspective, we can say that y hat is going to be equal to beta 0 plus beta 1 x1. That is the true prediction associated to those values. And of course, if we want to estimate beta 0 and beta 1, we will use beta hat 0 and beta hat 1. So the very first thing that we usually look at when it comes to the linear correlation between two values is the correlation coefficient. So let's look at that hypothesis test first. So somebody claims that the correlation for two variables is going to be equal to rho 0, and let's assume we're going to work with a two-sided alternative. Rho is not equal to rho 0. And again, remember that rho is always between -1 and 1, and as usual, we're going to estimate this with an unbiased estimator, which one can show is going to be equal to r, the sample correlation, and again, r and rho are always between -1 and 1, provided that your samples are real number samples. So the very first thing we need for this estimator is a standard error. So one can show that the standard error for the sample correlation coefficient is equal to the square root of 1 minus r squared divided by n minus 2. Now, if you are sampling from bivariate normal distributions, then the test statistic that you're going to be using is a t-test statistic. So a t-test statistic is going to be equal to, take a guess. So it's going to be equal to our point estimate minus the claim value of that correlation coefficient divided by the standard error associated to that particular point estimate. So that's going to be our t-test statistic. And the degrees of freedom we're going to be using here is going to be n minus 2. And you would interpret just like we did for all of our other hypothesis tests. Now let's look at the coefficients associated to our linear model. So for our slope of our line of best fit, which is typically represented as beta 1, So someone claims that beta 1 is equal to some number, say beta 1, 0. And let's assume we're going to be working with the two-sided alternative that beta 1 is not equal to beta 1, 0. So first thing we need is a point estimate, which is going to be beta hat 1. And that point estimate is going to have a standard error, which one can show is going to be equal to 1 divided by the standard deviation of our domain variables times the square root of the sum of squared residuals divided by the product of n minus 1 times n minus 2. So let's just recall what the sum of squared residuals is. So the sum of squared residuals is going to be equal to the sum from k is equal to n of our response variables, or our response variable values, minus the predicted values from our model, the difference squared, sum all of them up. Once you have your standard error, then we can compute again our t-test statistic. So our t-test statistic for the slope of our linear regression line is going to be equal to our point estimate minus the claim value of our slope divided by the standard error of our point estimate. And again, the degrees of freedom is going to be n minus 1, which is n minus 2. The last parameter of our linear regression model will be our intercept. Some people write it as b, some people write it as beta 0. So let's write it in the formal notation. So somebody claims that the intercept of our line of best fit is equal to something, say beta 0, 0, and let's assume we're working with a two-sided alternative. Okay, so that is our null hypothesis structure. So the first thing that we need is a point estimate. That's going to be beta hat 0. And then our standard error for beta hat 0 has a slightly maybe scary looking representation, but later we're actually going to find a very nicer way of representing this. But this is going to be, again, the sum of squared residuals divided by m minus 2 times another square root with 1 over n on the inside plus the sample mean, the quantity squared, divided by sx squared times m minus 1, which that denominator on that right-hand side is sometimes called the sum of squared differences for the x values. So we have our standard error, and again, our test statistic is going to be equal to our point estimate minus the claim value of the intercept divided by our standard error for beta hat 0. And as usual, take a guess at what the degrees of freedom for this is. This is going to be, again, v is equal to n minus 1, aka n minus 2. Now, in case you don't know how to calculate beta hat 1 and beta hat 0, let's just do a quick review of those just in case you don't remember. So beta hat 1 is going to be equal to the correlation coefficient between your x and y values times the standard deviation of y divided by the standard deviation of x. And beta hat 0 is going to be equal to the average of your y values minus the slope that we just calculated there times the average of our domain values. So that's how you would calculate, for example, our point estimates for beta 0 and beta 1, which is pretty nice. Now, let's just keep in mind that although all of these test statistics are very nice, sometimes the p-values can be misleading. So let's just close with this. So the p-values can be 1, misleading, 2, correct by chance, and 3, very incorrect, if any of our assumptions are not met. And what do I mean by our assumptions? Keep in mind, if you want to use a pooled variance t-test, then we require that the population variances be equal to each other or close to equal to each other for these linear regression parameters. And practically every zt chi-square f critical value based test statistic, we always assume that the populations we're sampling from are normally distributed. So if our assumptions are not met, our p-values can be misleading, correct only by chance, or very incorrect. So you have to be very, very careful. So one may ask, well, what if my assumptions are not met? Are there better alternatives for these test statistics and p-values? The answer is yes, but we're not going to get into them today, and we'll get into them next time. So for now, I hope you enjoyed, and I'll see you in the next video. Take care.